You know you want to learn about covalent bonds because I know you want to learn about covalent bonds. So we talked about ionic bonds, but we're going to talk about covalent bonds. Covalent bonds are between nonmetals. These are the strongest of all bonding that we see. So ionic bonds are created by ions. So they form salts, solid state, high melting point. Covalent bonds are going to be a little bit different. They are dealing with a nonmetal and a nonmetal. Ionic bonds are between a metal and a nonmetal. So positive and negative attract. Now, molecules or molecular compounds are going to be neutrally joined atoms to conform covalent bonds. So H2O is a covalent bond. Think about with covalent bonds, think about uh, ionic means to take away or to give. Now, if you were in kindergarten, it's not very thought of to take something from somebody. It was nice to give, but it was not nice to take. So when we're in kindergarten, they tell us it's nice to share. So sharing is what we're looking at in covalent bonds. So sharing those electrons is what's going to create these bonds. Because of the sharing, and we're still getting to the octet rule, so you're still getting to the noble gas correlation configuration. Uh, you are still going to have to share between them. So that means I can share, if I share my sandwich with you, we both get a sandwich basically. It's not I get half, you get half. We both share that sandwich. If we are sharing electrons, we're both getting to use those electrons. It's kind of like if you share headphones with somebody. I realize that we can't very well do that much anymore with COVID. You're both getting to hear the music. That's a better example than the sandwich thing. But because you're both getting to hear the music if you share your headphones. So think of the electrons more like the headphones in this situation. So covalent bonds are like sharing headphones. The types of molecules are you have monoatomic, so you have one atom. Diatomic are when you have two atoms. Uh, so remember, these show up as your diatomic. And remember the trick I told you, they create a 7 plus hydrogen on the periodic table. So the characteristics of the molecular compounds is we have low melting and boiling points, so you're going to have a lot more gas. Think of it this way. When you think of the carbon dioxide, you're going to see that as a gas more often than not, because when you think of carbon dioxide, you think of what you breathe out. Now, there is water, because water is actually more often liquid or gas than it is a solid. So think of the low melting point for that. You can actually melt it in your hand because that's how you actually are more, you have a higher temperature than the melting point of ice. They are not very strong and they are formed by all nonmetals. So when we use the prefixes for covalent bonds, we talk about moly, di, tri, and tetra. Now, poly meaning many, but once we get past four or tetra, we're getting two different names, but we'll worry about that later. So I just want you to memorize mono meaning one, di two, tri three, tetra for four. Tetra might be the only one that you don't realize, but think of tetra as in Tetris. So each of those blocks have four sides, so tetra. Now your molecular formulas. So chemical formula of a molecular compound shows how many atoms of each there are. So for instance, like we talked about with ionic compounds, you have to have multiple to make them balance. So in this case, we are combining them to make them balance. So there are two in H2O, there are two hydrogens for every one oxygen. In CH3, you have one carbon for every three hydrogens. And then in 2 in H4, that means that you have 2 in front of it. So you're multiplying everything by 2. Your nitrogen is going to have 2 because 2 times 1 is 2. And then your hydrogen is going to have 8 because 2 times 4 is 8. So when we put that number in front to balance these equations, which we will worry about here soon and not this chapter because we're trying to shove everything into it all at once, the 2 in front or the number in front multiplies the entire thing on each one by whatever their coefficient is, or whatever their smaller number is. So the octet rule still works in covalent bonding. So sharing electrons allows us to get to that octet rule. So if we're sharing the music that we're listening to, we're both still getting to hear it, but we're both using that music in our ears. Sharing occurs in the outer orbitals just like the ionic bonding. So valence electrons are still important in this. So that's where Lewis dot is important. So electrons are being shared between the nuclei of atoms of each. So we're always sharing our valence electrons. Single covalent bonds is one molecule is share one pair of each electron. So in halogen, they will create, all the halogens will create a single bond. So when fluorine is shown as F2, it is creating a single bond to share those outermost electrons. Now, double bonds, these are going to be shared between two pairs, so 4 total. So the group 16 is where we see these because you have 6, so they need to share those double. So oxygen O2 is going to share 4 total electrons between the 2 different oxygens. So that means you would see a 1, 2, 3, 4, 1, 2, 3, 4, and then 2, 4. So 4 plus 4 is 8, and 4 plus 4 is 8. Triple bonds. This is what we see in nitrogen. So nitrogen is the one we'll see this mostly in. A triple bond is a very strong bond. It's very hard to break a triple bond. So this shares 3 pairs of electrons, so 6 total. Think of pairs as 2. 2 is 2 pairs. 2 times 3 is 6. So that means we will see this triple bond, and you'll see 2 on the outside of these, and in 2 is where we see this happen more often than not. So Vesper. Vesper means valence shell electron pair repulsion. So the repulsion between electrons causes the molecule shapes to adjust, and so that the electrons stay far apart. So even though we have a shared electrons, we still want to keep the electrons as far apart as possible. So we see the different shapes of these electrons. So a nonpolar bond, this is where electrons are pulled equally away from each distance or each nucleus. A polar bond is where we see that they are unequally. So this results in a positive end and a negative end. So this means it is common found in hydrogen fluorine. So this is meaning that we are creating a bond to where it is more positively towards one end than the other. This is called a polar bond. So you'll have a positive end, which in this case would be our hydrogen, and fluorine would be our negative end. So that's where we're seeing that. Molecular attraction, so van der Waals force attraction between polar molecules. This is a very weak attraction. A hydrogen bond is attracted to unshared pairs of electrons, and a network solid is covalently bonded throughout. So this is very strong, high melting point. This is where diamonds are seen. So the carbon-based small network solid is going to be a diamond. We use diamonds for a lot of industrial purposes. It's pretty awesome to see the strength of what diamonds can do. Remember, I went over hydrogen bonds a little quick. So attracted to unshared pair of electrons, of course, it's going to involve hydrogen as well. That is all for today. If I went too fast, I apologize. This will be your last lecture for this week, or for this semester, actually, and we go into finals next week. All right. Good luck. I'm glad that I was able to keep it under 10 minutes, and I hope that you find my voice entertaining and soothing at the same time. Have a great day.